Here's a system of 3 blocks, 2 pulleys, and 2 strings. It looks like it should take a pile of information to solve, but the strings can't stretch. That single fact, a length that cannot change, is enough to lock the 3 blocks' accelerations together before we write down a single force. Let's turn a constant length into a rule about acceleration. Start with the geometry. An upper pulley is fixed, its center never moves, and the lower pulley, which we call P, hangs from a string and is free to ride up and down. Block 1 hangs on the other side of the upper pulley. Blocks 2 and 3 both hang from the lower pulley. Put the origin at the center of the upper pulley and choose downward as positive. Then Y1, the Y2, and Y3 locate the 3 blocks, and Y sub P locates the moving pulley. String A runs over the upper pulley. String B runs over the lower one. Both pulleys have radius r. Look at string A. It runs from block 1 up over the fixed pulley and back down to the movable pulley P. Its length is Y1 plus Y sub P plus the small arc of rope that wraps the pulley, pi times r. Here is the key move. The rope cannot stretch, so this length is constant. And the constant has a second time derivative of 0. So take the second time derivative of the whole length. The arc term, pi times r, is fixed, so it drops out. What remains is the second time derivative of y1 plus the second time derivative of y sub p equals 0. But a second time derivative of position is just an acceleration. So the acceleration of block 1 plus the acceleration of the pulley equals 0. In other words, the pulley's acceleration is minus the acceleration of block 1. When block 1 drops, pulley P rises by exactly the same amount. String B is more interesting because it runs over the pulley that moves. It goes from block 3 up around the lower pulley and back down to block 2. Measured from our origin, the two hanging segments are y3 minus y sub p and y2 minus y sub p plus the arc pi times r. Add them together. The length of string B is y2 plus y3 minus twice y sub p plus pi times r. Notice the factor of 2 on the pulley coordinate. Lowering the pulley by 1 unit shortens both segments at once. This length is constant too, so take its second time derivative and set it to 0. That gives the acceleration of block 2 plus the acceleration of block 3 minus twice the acceleration of the pulley equals 0. Now substitute what string A already told us. The acceleration of the pulley is minus the acceleration of block 1. And there is our constraint, the acceleration of block 2 plus the acceleration of block 3 plus twice the acceleration of block 1 equals 0. Now the forces. Draw a free body diagram for each moving object. Block 1 feels gravity pulling down, mass 1 times g, and the tension in string A pulling up. Blocks 2 and 3 each feel their own weight pulling down, and the tension in string B pulling up. Because the strings and the pulleys are massless and frictionless, the tension is the same all along each rope. One value, Ta, everywhere in string A, and one value, Tb, everywhere in string B. Finally, the moving pulley. String A holds it up with tension Ta, while string B pulls down on both sides, so the two downward pulls add to twice Tb. Apply Newton's second law along the downward direction to each object. For block 1, its weight, mass 1 times g minus the upward tension in string A equals mass 1 times its acceleration. For block 2, mass 2 times g minus the tension in string B equals mass 2 times its acceleration. For block 3, the same form, mass 3 times g minus the tension in string B equals mass 3 times its acceleration. Now the pulley, it is massless, so the net force on it must be 0 no matter how it accelerates. The two downward pulls of string B together twice T sub B minus the upward pull T sub A equal the pulley's mass times its acceleration, but that mass is 0. So twice the tension in string B equals the tension in string A. A massless pulley forces that fixed ratio between the two strings. Count what we have: the constraint, 3 block equations, and the tension relation. 5 equations for 5 unknowns, the 3 accelerations, and the 2 tensions. Solve it. First use T sub A equals twice T sub B to remove T sub A from block 1's equation. Then solve each block equation for its acceleration. Block 1's acceleration is g minus twice T sub B over mass 1. Block 2's is g minus T sub B over mass 2. Block 3's is g minus T sub B over mass 3. Feed these 3 into the constraint, block 2 plus block 3 plus twice block 1. The 3g terms combine into 4g, and the tension terms collect into T sub B times the quantity 4 over mass 1, plus 1 over mass 2, plus 1 over mass 3. Set that equal to 0 and solve. The tension in string B is 4g, times mass 1 mass 2, and mass 3, divided by mass 1 mass 3, plus mass 1 mass 2, plus 4 mass 2 mass 3. And the tension in string A is simply twice that. Now back substitute the tension to get each acceleration. Let the denominator be mass 1 mass 3 plus mass 1 mass 2 plus 4 mass 2 mass 3. Block 1's acceleration is g times mass 1 mass 3 plus mass 1 mass 2 minus 4 mass 2 mass 3, all over that denominator. Block 2's acceleration is g times minus 3 mass 1 mass 3 plus mass 1 mass 2 plus 4 mass 2 mass 3 over the denominator. And block 3's acceleration is g times mass 1 mass 3 minus 3 mass 1 mass 2 plus 4 mass 2 mass 3 over the denominator. One check before we trust these. Our constraint said twice block 1 plus block 2 plus block 3 must be 0. Add the 3 numerators with block 1 doubled and every term cancels. The mass 1 mass 3 terms sum to 0. The mass 1 mass 2 terms sum to 0, and the mass 2 mass 3 terms sum to 0. The acceleration satisfies the constraint, so the algebra holds. Step back and see the method, not just the answer. Whenever a rope can't stretch, write its length, declare that length constant, and differentiate twice. A constant's second derivative is 0, and that hands you a relation among accelerations. A moving pulley brings in a factor of 2 because it changes 2 segments at once. A massless pulley gives you a bonus equation, a fixed ratio between the tensions. Then it is just bookkeeping, as many equations as unknowns, solved together and checked against the very constraint you started from. That is the whole game with pulleys. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.